Continuing our discussion on time series, we had said before that regression may not be the best solution for predicting time series because of the violation of assumptions, specifically the independence of residuals. However, it does create a basis for us, and there are techniques that we build upon much later on to make regression work, and it is a very effective method. So data in business settings will follow a trend pattern. Now, if you consider that trend pattern as a linear line, then it kind of would make sense in some way that the regression equations would work, considering it's a linear line. So whether we're looking at a stock price, revenue projections, economic data, we are going to have some trend pattern. And our goal with time series is to break the data up into key components, a trend and some variation, and later on some seasonality. The trend is the general upward or downward direction of the data, and we will use regression to help explain the trend as a single independent variable. So our single independent variable will be time, there'll be a beta coefficient, and of course there'll be an intercept that will be provided. In general, our trend models could be linear or exponential, and all the other techniques that are in regression are applicable. So the best way to understand the linear trend is to understand that a change over each period is constant. So we're saying that a prediction changes over a constant amount each time, say $10 each period. So in time 1, it'll increase by 10. In time 2, it increases by 10. In time 3, it increases by 10. And there you see that beta coefficient multiplied by the time variable. So this is very similar to our regression equations, and that is exactly what the regression equation is. The alpha term is the intercept, and generally represents the expected value of the time series at time 0. The beta term is the rate of change for each period. So when beta is positive, the trend is upward, and when beta is negative, the trend is downward. And when we graph our time series, it becomes clear to see whether a linear trend model will work or not. Now, given a set of data that we talked about before from NASDAQ from February 13th to March 28th, we can chart the data and see a clear trend line. So the blue line represents the actual data points, and we can see that our red line that's created is a trend line, and that was the actual trend line that was created by Excel. And you can do that by adding the trend line in the graph options when you create the graph, and it will give you the actual formula. Therefore, to make an estimate for prediction, we can use a simple regression line with t as the time from 1 to 31, the number of days in the data set, and add a column to our existing set with the sequential numbers 1 to 31. So to the right of where it says NASDAQ, it would have 1 through 31. And you'll see this in the corresponding Excel file. And then we conduct a normal regression. We use our data analysis tool, conduct the regression, and find the formula for the trend line, which is given by the summary output. And we say that the predicted value of y, which is denoted by y hat, is equal to 1146.19 as the intercept, plus 19.56 times the period. And we get those from the coefficients in the summary output table. Finally, you would then want to create your chart of residuals to determine how well the model worked. Now, using our regression knowledge, we can go further with the interpretation and understand some of the other pieces. So remember that adjusted R squared is how much the variance in y is predicted by the model, or the x's in this case. And we can see by the summary output that the adjusted R squared is very small. It's only 0.08, or 8%, not very good. In this case, we look further, and the model may not have utility because the p-value from the ANOVA table is 0.06, and that's greater than our critical value of 0.05. So this may not be a good model, may not have utility. If we further look at the coefficients, the coefficient for the period x1 is 19.56. Now we can interpret that as saying that each period we can expect the prediction to increase by 19.56. So every successive period will increase by 19.56. However, the p-value for that coefficient is not significant. It also is 0.0656. That means that the p-value is not less than 0.05, and so we cannot reject the null hypothesis that this coefficient is equivalent to 0, and thus we say it's not significant. So in general, this model in particular does not help us, but it's a good example to see how we can interpret the various components. Now, if you go back to the chart up here at the top, you'll notice that the red line tries to cut everything straight across. But there's a lot of variation that's occurring. It's going up and down over this line. And the problem here is that we probably have a significant increase in errors. And the model itself is not able to really account for some of those errors. So we want to be real careful about how we conduct regression for time series applications and make sure that you had looked at the residual graphs to determine whether or not the residuals are normally distributed, whether it has a constant variance, and whether or not the residuals are independent.